recording and share my screen. And since it's just the three of us right now, we'll start with the question about it was problem number 23, right? That 24, the concurrently, yeah. Yeah, so this question's posted to GitHub issues, and we'll go ahead and go over it right here. Again, I have on the left-hand side are three terminal windows opened up to pSQL, and they're all connected to the same database right now, and that database is empty. And I'll use the bottom two for the session 1 and session 2, and then the top one up here for some debugging things. And we'll probably see maybe or expand on some of the debugging things that we talked about last time in order to see what's weird about this problem 24 right here. But let's go ahead and do so create table T, int, like that, line 1, and then begin, semicolon, forgot the semicolon, and then lock table T in row exclusive mode like this. And so now we're at line 3. We've done 1, 2, and 3, and this is the same so far for problem 23 and problem 24. And before going on to line 4, I want to take a look at our PG locks table. That's the table that we use for the debugging. So start \d PG _ locks. Let's remind ourselves what the columns were for that and make that a little bit more readable, a little bit bigger still, like that. So there's a bunch of columns over here. The ones that we're interested in are this relation column. Its type is an OID. So if I just do select relation from PG locks, we're going to get a bunch of numbers. OIDs are numbers, but we can convert that to the name of the relation with the :reg class like this. And then the other column that we're interested in was the mode column like this that tells us the how it's locked. And finally, we have these sort of empty ones here that don't correspond to any particular relation. And that's because in the PG locks table, there's this lock type. We've only talked about locks on relations, but there are locks on other things as well. So we're going to filter this out where lock type equals relation like this. And so these are the locks that we have so far. And in particular, this session down here has created this row exclusive lock. So right now, we're looking at the notes, problems 23 and 24. And one other thing maybe to help us in our debugging, there's a PID column. PID stands for the process ID, tells us which one of these processes is going to be acquiring this lock. And so this one down here is process 74. It has the row exclusive lock right here. And then this process up here at the top, our debugging one, is number 88. And again, we said that every time you select from PG locks, you'll get some sort of lock on the PG locks table because the select query creates this access share lock. Okay, and so then the question is, if we look up in our documentation for all these problems, we have this documentation over here that has this table that explains how the different locks conflict. And if we look at the creating index, create index right here, this will create the share lock. And then the create index concurrently, that creates this share update exclusive lock. And we know that by looking up into this section up here. Share update exclusive talks about create index concurrently right here. And then share create index without concurrently. And so the share lock share lock conflicts with the row exclusive lock, and so we should expect things to block. And so let's go ahead and down here, create index requires that share lock. Let's try that. Create index on T of A, like that. And we can see that it looks like it's blocking. And if we come back up here and rerun this, then we can see that we've now have a new process. Process 81 has acquired the share lock on relation T. One other thing for us to check at this point, I want to do \dt like this. It'll show us here's the table, and there is no index created. If up here I type not there, commit. Down here I type commit right here, then this one will terminate. This index is created now. And up here, if I type \dt, we can see that there is in fact an index listed here. Starting maybe the end of this week, but definitely next week, we'll be talking about exactly what these indexes are and how they work to make our queries faster. But at this point, they're just the results of this command right here. I'm going to go ahead and drop our table T so that we have back to a plain state. And then we'll take a look at problem 24 down here. So create table T a int like that, and then a begin, and then a lock table T in row exclusive mode like that. And then create index concurrently on T down here. Create index concurrently on T of A like this. And I hit enter, and it looks like it's blocking. The question that was posted on GitHub is that, so create index concurrently, we looked that up. It creates the share access exclusive lock. There we go. The share update exclusive lock. And if we look at this table here, share update exclusive does not conflict with the row exclusive lock. So is this in fact blocking? Why is it saying that it's not blocking here, but it looks like it's blocking in the terminal over here? And the answer is that it is actually not blocking. It is just a really, really, really long running command. So this up here is blocking, so it should get circled. This one down here, it looks like it's blocking, but it's not blocking. We'll see evidence of that here in a second. Not blocking, just long running. And so up here now, if I do the \d on T, we can see that this index has already been created. So when we did the create index command, this index was not created yet until after the commit happened, because the create index command had not run until after the commit happened in session 1 right here. In session 2 down here, this command is currently running. It's already created this index command. So that's one piece of evidence about why this command is actually running right now. Let's take a look at the our debugging command up here, and we see that it has the same locks listed as before. Now it's the share update exclusive lock in process 81 instead of the share lock. I want to see one more column from this table called the granted column, comma granted, like this. Granted means that the lock has actually been given, which means that the command is currently running. Anytime you see a true here, or a T, the T stands for true. So that means that all of these locks have been given. So the commands associated with those locks have actually been run. So the row exclusive lock corresponding to this right here has a true, so it has been run. The share update exclusive lock corresponding to this command right here has a T, so it has actually been run. I'm going to press Control-C right here to cancel this statement so it doesn't finish running that command. You can see that the lock up here is gone. And I'm going to replace this with the create index command on T like this. Now, this command is blocking. It's creating the share lock right here. The share lock conflicts with the row exclusive lock. And if I come up here and rerun this command, you see that there's an F right here that it's not been granted. And so it is, in fact, blocking. So this is a I don't know, it was maybe a trick problem. I don't think I intended for this situation to actually occur on this this problem set, but it did. And so it's the way that we know that it is not blocking was because it had a T right here instead of an F. A blocking means that it will have an F. So this is the way for any command to check if it's actually blocking or not blocking. It's sort of a convenient method down here to see if it goes on to the next line, but it could just be a long running command. It doesn't necessarily mean that it's blocking the fact that it's not going on to the next line. This is the sort of actual ground truth of how you check if something's blocking or not blocking. If it's an F right here, that means it's blocking. Anything else, it means it's not blocking. Any questions about those two problems, this 23 and 24?
When you're referencing the table, I'm supposed to look at row exclusive mode for the existing block since you were referencing share block and share update.
Oh, did I? Yeah, I was looking at it backwards. You're right. The existing mode lock was row exclusive, and we were looking up at the share and the share update exclusive. So I guess it turns out that this table is actually symmetric, so it doesn't matter which way you go. But you're right that I should have said that the existing lock was the row exclusive, and we were looking up share and share exclusive. Good question. Any other questions on these two problems? Okay, we're going to revisit this, finish this problem set today, but before doing that, a few quick announcements. So the week 10 folder has been posted. Inside of there is a new Twitter Postgres assignment, which is due on Sunday of this week. We will probably finish talking about what you need for that assignment today, but if not, we'll finish that up on Wednesday. Other announcements on the midterm. I mentioned last time that I made a mistake with the initial grading, and I really do apologize with that. I know when I was a student, that was always super frustrating for me when grade sort of mistakes were made, and it took a long time getting a real grade back, so I do apologize for that. But a lot of people, about a third of the class, got points back, either 10 points or 5 points if you missed 10 of the points originally. So you can take a look at that to see if you got those points back. The quiz that we'll be having on the this problem set that we're finishing up today will be a week from today. And the format of that will be the same as the previous in-class quizzes that we've had, where I will be here about a half hour before start of class, so you can come as early as you want and have as much time as you want. Time shouldn't be a factor on this quiz. Then the homework due at the end of this week, and a handful of people have emailed me about extra credits, and apologize that I haven't replied to you individually, but those questions about getting like individualized extra credit, you'll need to talk to me in person about that so that we can talk back and forth about exactly what we should do to do an extra credit that fits your particular circumstances. So if you would like extra credit, please see me in person at some point. And then, yeah, again, we'll be finishing up the last week's notes today before going on to new material. But the idea of the new material for this week is that we're going to be talking about how these locks are actually like physically implemented in Postgres. And that will tell us about disk usage of tables, and it will lead us into this discussion about indexes, which will be used for talking about the different algorithms that will be making the actual SQL select statements fast. So all this, yeah, all of this, the point of all this is so that by about the end of next week, we will have everything that we need to know to make all of our SQL select statements like take microseconds, be essentially instantaneous. Any questions about anything administrative before we get into the material for today? See, is everybody awake? Do we have good weekends? A couple head nods. Nobody shaking your head, nobody had a bad weekend. We're all ready to discuss deep technical concepts. Let's see, before we get to the actual, finish up the PDF file, I'll finish up the GitHub notes to make sure we don't miss that. We'll wean ourselves into the harder technical material. The last time we talked about, there's this idea of ACID databases, and these are the four sort of keywords. We've talked about atomicity and isolation. That's what transactions are giving us. And then this idea of consistency, we started talking about that last time with the unique constraint and how that works. We'll finish that discussion up today with the foreign key constraint. And then the thing that we're not going to talk about is durability. So let's just, yeah, I guess we'll do a quick overview of durability here, but we're not going to talk about like how it's actually implemented. But the idea of durability is that in a database system, if there's a disaster like a power failure or a hardware failure, or like somebody takes an axe to the computer and just destroys the computer, durability of Postgres guarantees that you're not going to lose data. And so this is implementing durability is a hard CS problem, which we're not going to talk about, but Postgres does handle it for us. And one of the things that I don't like about NoSQL databases is that they don't support durability, so things like Mongo and Cassandra. And Mongo in particular is famous for claiming that they have durability, but independent tests demonstrate that they don't. And Mongo has, I don't want to say lied about those tests, but basically lied about those tests. This durability is important because websites like The Guardian used to use MongoDB to store their actual articles, but they have forever lost articles because MongoDB did not actually store them correctly. And so they switched over to Postgres because it has these ACID guarantees that you're not going to lose the data that you put into your database. MongoDB does not have that sort of guarantee. Because MongoDB doesn't have those ACID guarantees, it can be faster in some situations. But if you really, really need that speed, you can actually turn off different safety features in Postgres to get that speed. It's just something that you would never want to do in actual real world scenario unless you really, really know what you're doing. And then last thing is so we've been talking about transactions. If there's one sort of like technique with transactions that you want to remember, it's that anytime you're deleting something from your database, just first make a transaction, then type your delete command. And because you might delete the wrong thing, you might type in the wrong command. And if you're not in a transaction, you can't recover that data. But if you are in a transaction, you can easily recover that data. And there's a lot of sort of horror stories about junior devs who have accidentally deleted the production database because they were not in a transaction when they typed their delete command. Any questions about anything before getting into the PDF file? Okay, so last time we talked about these implicit locks, which we went over again just now. And then we talked about it was a little bit out of order. We did the row level locks, and then we went back up and did the unique constraints. And the thing that was special about the unique constraints is that they combine a insert with a select statement. That if you're going to insert into the database and it has a unique constraint, you have to first somehow select to check if that row exists to know whether you can insert or not. And that causes the potential for deadlocks. So some of these problems down here with two tables with two different unique constraints will cause deadlocks, and some of them won't. And that'll be a particularly important thing, a particularly important concept for your programming assignments. And so it will also be something that will definitely be on the quiz somehow next week. But now we're going on to the foreign keys. Foreign keys 1 down here. So first of all, in this problem 51, we have two tables again, T and U. T has a unique constraint and U has a foreign key where this B column references the A column in the T table. Anytime you have a foreign key in Postgres, it's required that the thing that's being referenced have a unique constraint on it. So we were just talking about unique constraints can be a big source of deadlocks. And so because foreign key constraints require unique constraints, foreign keys can also be a big source of deadlocks. So anytime you see either of those two things, you should be like scared about deadlocks possibly happening. So let's go ahead and let's see. I'm gonna reset the problem down here. Abort. Make sure we're not in a transaction. Let's make sure we delete all our tables, drop table of T. And then, yeah, there's a good question before class about, okay, our screens over here are pretty messy right now. Is there anything that I can do to clean them up? There's a number of things that you can do to clean them up. If you press Control L, that will clear the screen. I never remember Control L. What I remember is that if you do the backslash and then an exclamation point, whatever you type here is going to be a bash command. And so you can type like the clear bash command to reset things. That's easier for me to remember. Okay, so session 1 down here, create table T, A, int, unique, and then create table U. B, int, references, T of A, like that, and then begin. So that's the first 3 lines of problem 51 right here. And then we're in a transaction on line 4, so begin over here. And then here, what we're seeing is that if we insert into T values 9, so just a standard insert into this T table up here, because we're isolated between these two transactions, because we're isolated between this transaction and this transaction over here, when we try to do this insert into U, values 9, this insert into U requires that we have a corresponding entry in the T table. But we're isolated from this transaction over here, so we don't know, this transaction has no idea that this is potentially going to get inserted. And so when we hit enter here, we get this error message saying that we violate the foreign key constraint. And so this is going to be an X through it for what you need to do for the quiz, because this throws an error for us. And then keep going on the problems, the commits, just go ahead like normal, like that. Any questions on why this errors? Okay, the difference between this problem and the next problem is that down here, line 4 does not happen inside of a transaction when we do this insert, so the effects will take place immediately. And so because over here, our isolation level is set so that we see the effects immediately, this will not error. If I were to change the isolation level, so the isolation level section tells us how to do that. Doing something, here it is, doing the begin isolation level repeatable read, that can have an important impact on how these foreign keys work with these inserts. That we would not be able to see this insert right here, or sorry, this transaction over here would not be able to see this insert if we were in the repeatable read mode. And so you'll need to be careful on the quiz about what sort of isolation level you're in, whether you can see the things that have been inserted or not. Any questions about that? Uh, 52 will succeed successfully. No problem here. And the reason is because this insert right here is instantly visible. And so because that's been inserted before into T before we do something into U, there won't be a problem with the foreign key. We drop table T, drop both the tables. Create table T, A int unique. Create table U, B int references T of A. And then down here, begin, up here, insert into T, values 9. Down here, insert into U, values 9. Oops. Getting an error just because I can't type insert. In order to, let's see, go ahead and fix this typo. I don't think this has come up yet in class, so I'll demonstrate this, that now I have a correct statement right here. Still getting an error though, because as soon as in a transaction you have one error, everything else is automatically going to error. So I'll have to abort this and restart it to get this to actually run. And here you can see that it's able to see this value here, so it doesn't, no error. So the next foreign key is where things get interesting, is when you have, so let's see, let's go ahead and delete from T, abort here. So we have an empty, our two tables are empty. Let's insert into T, values 8, insert into T, values 9, that's lines 3 and 4, and then line 5, begin. Down here, line 6, begin. And now we're getting into row level locks with our foreign keys. And how do those work? Up here on line 7, we're on line 7 right now. We've just done the 2 begins. Line 7, inserts into U, values 9, like this. Anytime you do an insert into a column that has a foreign key, that insert first has to do a select into the other table. So up here, let's rerun our PG locks command to see what sort of locks we currently have. And you see that we have a row share lock on T caused by this insert right here. This row share lock on T is because there is a select statement that this insert command has to run in order to see, does this value 9 exist in the T table? And the select statement creates the row share lock. And then the insert statement itself creates the row exclusive lock. Down here, when we do the delete from T where A equals 9, delete from T where A equals 9 right here, this is going to be on the same row that the share lock was created in this insert command right here. So I'll hit enter, and we'll see that this is going to block. Up here, run this. We have our, so PID 81 is doing the row exclusive lock. This delete right here created the row exclusive lock. So row exclusive. This insert right here created the, was also a row exclusive lock on U. And the row share on T. Because this right here, this row exclusive is on table T, we can ignore this, this row exclusive on U. That doesn't matter. It's on 2 separate tables, so that doesn't affect whether it's going to block or not. And here we have the row share and the row exclusive lock. If we come over to our documentation, the row share and the row exclusive, they never block each other directly. They don't block each other at the table level. So they're, we see that a block is in fact happening down here, but it's not because of a table level block, it's because of a row level block. The select statement that's being run by this insert right here is what it looks like is, so it'll be select star from U, sorry, from T. We're selecting from the references table right here. And then it adds the for the weakest possible blocking mode for key share right here. For key share. And so because we have this blocking for key share right here, and then when we do the delete, it's going to happen on the same row. So we need to check out what kind of block does a delete create, or what kind of lock does a delete create. And the delete, here it is, delete creates the for update lock. And the for update lock, down below, the for update lock conflicts with everything. In particular, it conflicts with the for key share. So again, this is a symmetric table, but doing this properly, the original requested lock mode was the current lock mode was the for key share, and then our requested lock mode was the for update, and so we get the X right here, so it blocks at the row level. And so because it blocks, we'll circle that right there. And then committing after both of these two things commit, it will it'll update and add the information to the table. Let's go ahead and do that. Commit. Oops. Sorry, we'll not be able to add this to the table because the delete right here. As soon as we commit on line 9 down here, that inserts into U values 9, inserts into U values 9. This, we can't delete from T then because that would violate this references. The U inside of here requires that there be something in the T table. And so this originally blocks, and then after this commits, we can't do this delete anymore without violating the constraint. So it also errors, blocks and errors. And then the final commit down here does nothing. Are there any questions about that problem, Joe?
Could you go over how you do where the select star from T for key share came from?
Good question. The question is, how did I know that this did a select star from T for key share? And the answer is that you would have to look up in the documentation for the foreign key, this references right here. It doesn't actually say anywhere in here that the select for a foreign key allocates this, but that's what it does. Same with the unique. All the selects that happen for one of these constraints do add the for key share as the type of row level block that it does. Yeah, so in terms of like what row level locks will you need to be aware of, the unique and the references create this for key share lock. And then if you specifically specify one by actually adding one of these to the end of your select statement, then it will lock the appropriate rows with that particular lock. And then if you use the delete does a for update, and the update does a for no key update lock. Those are the situations that you have to know about. So stating that again is that the select statements that correspond to a constraint do the select for key share, and the delete statements do the for update, and the update statements will do the for no key updates. Yes, yeah. The update could also, depending on your particular columns, do a for update, but that's not going to, the difference is not going to come up. Good question. Any other questions about this problem 53?
Let's start from E. Does it have like a where clause, or
Sorry, yes, thank you. I didn't write the where clause. The where corresponds to the foreign key reference. So it would be, oops, where here we're inserting the 9 into the B column. That references the A column in T. So it would be where A equals 9. It's a good question. And so we're getting this this lock right here on number 8 specifically because this delete is interacting with the same row that this select is interacting with. Any other questions on this problem? Okay, the remainder of the problems in this section right here are all, they just have slightly different conditions over here. So here, the condition where A equals 8 doesn't match this row that's being inserted. So after you work through it, you're not going to get a block. Here, 55 and 56 have aborts instead of commits on the left-hand transaction. So that will affect the whether these operations over here will succeed or fail. And then the other problems just are happening in different orders. So testing your knowledge of the isolation between those transactions and how the different ordering will affect that. Any questions on any of the foreign key constraints? Okay. The last section here, deferring constraints. So by default, we said that this unique constraint and this foreign key constraint require us to do a select whenever we're doing one of these like insert or update commands to make sure that we're maintaining our the integrity, the consistency of our tables, of our database. And Postgres gives you the option of specifying when you want those checks to happen. By default, they happen immediately before the command. So by default, yeah, it happens immediately. That when we have this insert right here, inserts require the select statement again, and it happens before the insert. But if we add this long clause right here, so deferrable, initially deferred to any constraint, then this will cause the check to happen at commit time rather than, so check at commit time. In particular, running the corresponding select statements at commit time rather than at the location of the insert. So let's see what that's going to look like. Make sure we're not in a transaction for these. Drop tables UNT. Let's clear these. And then, so create table T. We say a int unique like this. So I'm going to start without the deferrable, initially deferred addition to the constraint down here. Hit enter like that. And then begin our transaction, insert into T values 8 like this, insert into T values 8. By default, the check happens instantly, immediately before the insert is run, and so we get an error. So if we did not have this deferrable initially deferred, then we would put an X through line 7 because that would generate an error. In this case, though, for problem 59, we do have this deferrable initially deferred. So let's redo this problem. Drop table T with this additional clause added. So create table T, A int unique, deferrable initially deferred. I spelled everything correctly. And then begin. And then insert into T values 8 like this. So no problems up to line 6, same as we had before. But then if I rerun this insert into T, nope, it doesn't throw an error at all. Because we haven't done the consistency checks yet. We haven't run those select statements yet. The select statements will get run as soon as I run this commit right here, and that actually causes the error. So in this case, with the deferrable initially deferred, you put the X on the commit line. It's the commit that causes the error. Without the deferrable initially deferred, it would be line 7 that causes the error. Are there any questions about that?
What's the motivation for using?
Yeah, great question. The question is, what is the motivation? And we'll see that in your homework assignments, in order to make our insertions faster, we're going to reorder the insertions in a certain way to minimize the number of insert statements that need to be called. And after we do that reordering, it won't be able to pass the consistency checks immediately. You'll have to defer it to the end of the transaction to have it pass the checks. So it's, yeah, I mean, this is a very artificial situation right here just to illustrate what's going on. But when you have bigger things, I usually find that this is the situation that I want, the deferring the check until the commit time, because that gives you more flexibility in ordering your SQL statements. Good question. Any other questions?
So, but the commands that succeed, they're like they all succeed, right? Like they don't get that error.
So in problem 59, as it's written, line 1 through 7 all succeed, line 8 fails.
So we have sort of like 8
Oh yeah, so the question is, does it actually get inserted? And the answer is no, because of the atomicness of transactions. That if now we did a select star from T, there's nothing in there, because if anything related to a transaction fails, then everything related to a transaction fails. That's a great question. Any other questions about problem 59? Okay, yeah. So again, yeah, this is super artificial with unique constraints. It becomes less artificial with the foreign key constraints, because it might be more easy if we have the same situation between tables T and U that we had before, to have insert U into the database before we insert T. That our code might just have the values for U available before we have the values for T available. And so that's what these problems are demonstrating. Down here, so let's drop table T. We have empty database. Go line 1, create table T, create. Let's go ahead and clear it first. Create table T, A int unique. Create table U, B int references T of A, deferrable initially deferred, like that. And then begin. So I've done lines 1 through 6 up here in session 1 right here. Again, lines 2 through 5. They take up multiple lines in my session over here just to fit it on the screen nicely. But over here, I typed it in a single line. It's the semicolon, which really decides when a command is over or not over. Then line 7 over here. Also creating a transaction. Begin. And let's insert into U values 8. Insert into U values 8 like this. And you can see that this, it succeeds. That we did not run our select check into the T table. And so when we run this command right here, it just does the insert, and it doesn't care whether this value exists yet in the T table. Now, in session 1, let's actually insert it into the T table. Insert into T values 8 like this. And then line 10, commit that. And so because we've committed this, line 10, and because our isolation level over here allows us to see these commits that have happened in other sessions, we will now have access to the values in T, and the constraint will be satisfied. It was not satisfied when we first ran this line, but it is now satisfied. And so we run line 11 down here, run the commit, and everything works. If this was not deferrable initially deferred, then we would get an error on line 8 right here, because this would immediately be looking for the value in the T table. Any questions about that problem? Are these, well, rather than phrasing this as a question, I'll phrase it as a statement. If these problems are seeming like overwhelming, like there's a lot to keep track of, there is in fact a lot to keep track of, and so you should, yeah, it will take an appropriate amount of time studying in order to do well on the quiz. There is just a lot of very, very subtle things, and very minor changes in the code can have totally complete different outputs in what's going to happen over here. Any questions at this point? Okay, then the remainder of the problems are just doing variations on this theme right here. Problem 61, instead of committing over here, we abort. So this value 8 never actually gets added to the T table. Our transaction here is never able to actually see it. And so because of that, when we do the commit over here and it does the select to try to actually do the check, it's going to fail. And it'll be line 11 that fails and not line 8. Let's see. Yeah, and then I'll let you think about the next ones yourself and work through those. Any questions at all about, so again, the quiz will be a week from today. Any questions about what to expect at this point? Sure. Yeah, that's a good question. So like details about exactly how many problems there will be, and also how many points the quiz will be worth. I haven't decided exactly how many problems, but it'll be like between 3 and 5. And the number of points will be on the order of a homework assignment. So I'll have those exact details for you before the quiz on Monday, but roughly 20 points-ish and roughly 3 to 5 problems. Again, you have 10 minutes in class plus up to a half hour before class if you choose to take it. Okay, so yeah, all this material might seem at this point like extremely abstract, like what are the applications for all of this? And so it might be, that's potentially adding to the confusion about like, it's just feeling very unmotivated. And so the homework assignment this week, the purpose of the homework assignment, one of the purposes is to motivate this, this material here, but really the main purpose of this material here is to help us understand what's going to happen in the homework assignments. So I'll come over to GitHub, and then the homework assignment is, the repo is called Twitter Postgres Parallel. And in this repo, there are 6 of these test case badges, and 3 of them are already passing, 3 of them are failing. The ones that are passing correspond to sequential runs of various code, and the ones that are failing correspond to parallel runs of the code. And the goal of this assignment is the same as the goal of the last assignment, that we're trying to load up our Twitter database and make sure that we're loading things correctly. Inside of this SQL folder over here, we have the same SQL queries that we had for the last assignments. Now our data is stored in this data folder right here, and there's 10 zip files that are just truncated zip files from our Twitter database. And each one of these zip files has 10,000 tweets in it. So each one of these zip files individually is the same size as the zip file that we were working with last time. And so because we have 10 times the amount of data, the sequential tweet loading will take 10 times as long. But our goal now is to parallelize this, so all 10 of these data files will get loaded in parallel, and the runtime will not be any longer. It'll take the same amount of time. So we'll get 10 times speed up from our sequential to our parallel version. There's, so yeah, 3, well, let's see. Let's switch over. I'm gonna readjust these screens, getting out of here. We'll take a look at the assignment in the terminal next so that we can get a little bit more familiar with what to expect. And so in the week 10 folder, there's this Twitter Postgres parallel. So let's go inside of that. And then inside of here, the services, there's 3 folders. The PG denormalized and PG normalized folders are exactly the same as from the last assignment, but now I've given you a new one, PG normalized batch as well. The inside of the repository, the load tweets.py is my solution to the last assignment for loading the tweets into the normalized file. The denormalized one is still using that copy command in the special JSON loading techniques into Postgres. And then this PG normalized batch is using this load tweets batch.py file right here. And you're not going to have to, or I've given you basically what this file looks like. So vim load tweets underscore batch.py. And the basic idea of this file is that rather than loading the tweets sort of one at a time, in this load insert tweets function right here, there's a bunch of a bunch of lists, and we add all of the information to this list, to these lists that we're going to load in. And when we do that, so the loop looks essentially the same as before, but we're appending to those lists at each one of these locations where you used to be directly doing an insert into the database. And then down at the end of the file, this step 2 performs the actual SQL inserts. This bulk insert command right here inserts everything in this list into this table, everything in this list into this table. And by having these inserts, this will be just a single insert command. And so we make only a single connection to the database, have to transmit things over the network only a single time. And this will give about a 10 to 100 times speed up on your insertion before. So last time you saw that the PG normalized took a lot longer to load than the PG denormalized. In this case, the denormalized, it'll still be a little bit slower, but it'll only be about like 3 to 4 times slower rather than 100 times slower. So that's what what this extra normalized underscore batch system is for, is this extra batch loading. Any questions so far? Okay. So the tasks for this assignment is divided up into 3 parts. First, the setup, which is the same setup as you had with the last assignment. And in particular, the thing that you have to be careful of is with the docker compose.yaml file, and docker compose.yaml. All the ports are incorrectly specified at this point, and so you have to readjust those ports. Now there's 2 SH files that you'll have to adjust as well, the load tweets sequential and load tweets parallel, corresponding to the next 2 parts of the assignment. The sequential data loading should be super straightforward thing to do. You just adjust your load tweets sequential file. So vim load tweets sequential file. Adjust this so that anytime it's referring to the Postgres, it's referring to the appropriate port number over here. I've given you all those commands here, so you don't have to provide anything, just have to change the port numbers. And it'll run on every file in the data folder, just one at a time, one after the other. It's going to time all of these results, and the only thing that you have to do for this this first part, after you have everything working correctly, is at the very bottom of this this file under the submission, there's an elapsed time sequential. You'll have to put however much time it actually takes here. The PG normalized and denormalized for this one will be roughly 100-ish times slower than this. This one should be roughly 4 times slower than this. So doing the batch loading is a huge performance boost over not doing the batch loading here. The main things that you'll have to do are for the parallel data loading. And the parallel data loading is divided up into 2 sections, the denormalized section and the normalized section. The normalized one is the one that's related to locks. So we'll start talking about that one first. What we'll see is that with the unbatched version, there's actually no problems with locking, no problems with deadlocking. And so this will just work, won't generate any errors for you. Don't have to modify this code at all. The batched version, though, you will have to modify so that it does not get any deadlocks. So in order to make sure that it doesn't get deadlocks, you'll have to really understand the previous problems from the PDF about what causes a deadlock and what doesn't cause a deadlock. And then the sort of, I give you an outline of the things that you'll have to modify about your database in order to remove those deadlocks. But the basic idea is you'll have to remove all of the constraints. It's the consistency checks that are going to cause the deadlocks. And so you'll need to remove the unique constraints. If you recall, though, the main problem with that is the way we have our URLs stored in this database. They are stored fully normalized. And so we're using this get id URLs to convert a URL into an ID. This function depends on the fact that we have a unique constraint in the URLs table. I'll go ahead and open that up. Vim services PG normalized batch schema dot in this URLs table right here, we have this unique constraint on the URL. And the get id URLs function requires this unique constraint right here. Turns out to be impossible to implement that function without this unique constraint. So what you're going to have to do is you're going to have to actually delete this table and change how you represent URLs. You're going to have to denormalize your URL representation. And the way you're going to do that is every time down here you have something that references id URLs with one of these references like this, you'll have to change this. So instead of being a key into this table, you're just going to store the URL directly. So change the name of this column to URL, change the type from big int to text. And so you'll be storing the URL directly in the database here. There's going to be a trade-off in terms of the amount of disk space used because URLs can potentially be very long, so potentially store many, many bytes. The big int right here, though, is guaranteed to be at exactly 8 bytes. Every URL is going to be more than 8 bytes. So we're going to be using up a little bit more disk space in all of our tables that reference URLs. But the trade-off is that we won't be getting deadlocks, so things will be going much, much faster. So that's what these steps here are describing to do: deleting the URLs table, modifying id URLs big int to URL text, and deleting all the foreign keys that reference the id URLs. Since you're changing the schema, you'll have to change the Python file as well. And in particular, delete the get id URLs function. And any time where you were using the get id URLs to convert the text of the URL into a number, you'll just put that URL directly into the table. Once you properly understand what all this is saying, it's very few lines of code that need to be changed. Each one of these steps is less than 10 lines of code. The tricky part is just understanding exactly what it's trying to ask for. After you fix this unique constraint on the URLs, there's a number of other unique constraints that you'll have to handle as well. And so in particular, look for places where it talks about primary keys in addition to things that have unique constraints labeled. And you'll have to just delete the primary key, delete the unique constraint. And after you do that, you'll have to also delete the foreign key constraints because foreign keys reference those. There'll be a couple changes that you'll have to make in Python too when it'll be throwing some errors at you relating to expecting a unique constraint, but those errors should be easy to fix. Let's see, there was the question earlier about what's the motivation again for this deferrable initially deferred. All of these references, all of our constraints in this batch file need to have this deferrable initially deferred when these constraints are here in order for us to have this reordering to make things fast. But in order to make things parallel, you're actually going to delete these constraints entirely. Any questions about any of that? I realize that's maybe a bit high level or abstract feeling until you actually sit down and work through the problems. So if you run into questions, feel free to post them on GitHub or ask them in class. Any questions at this point? So,
actually, like in the schema, I'm wondering, do we always put the primary key at the top, even though it's like a big key and timestamp?
Question is, why do I have primary key or why do I have the big int at the top, and is this the most efficient in terms of the column Tetris? Yeah, so for the big int and the timestamp, turns out they both take up 8 bytes. So it's a little bit maybe weird that I have a big int and big int here with the timestamp between them, but it doesn't actually matter. When you change your code so that it uses the text value here, then this is sort of technically no longer the optimal location for the URLs to be stored in the table. And so it would be ideal to move this column down here somewhere at the end. But it's not strictly necessary to do that. So this is the, those are the changes that you have to make to the normalized data file. The last thing for us to talk about is what you have to do for the denormalized data. And in order to talk about that, let's go ahead and open up our load tweets parallel.ash function here. And so you can see that here I have fix me implement this, that you're going to have to write the code that goes inside of here. But this should be a, we'll talk about how to do that now, and it should be like a totally, I don't want to say, well, yeah, I think it should be an easy thing to do. The idea is that in, we're using this parallel function inside of bash or inside of the POSIX shell to parallelize our scripts, to parallelize all of our calls to Python. And so we're going to talk about how this parallel call works, exactly what it does, and how you'll use that up here to make your PG denormalized run in parallel. So parallel, first of all, I'll use the right-hand terminal over here to talk about parallel. Parallel, it's not built into bash. It's just a standalone executable provided by the GNU libraries. So GNU executable. Yeah, one of the things, I don't know if this has come up before, but so GNU, when it's pronounced like the animal, is a new. So there's news that are animals in the zoo, but when you're talking about the open source Libre software sort of movement, this organization, you pronounce the G, GNU, and so that's how you know that somebody's in the know about GNU. And what GNU actually stands for, it's a recursive algorithm. GNU is not Unix. Is what it stands for. The this parallel function, this parallel executable, what it does is it mimics the functionality of something called xargs. And so let's make this ps1 equals a little bit easier to read. So GNU parallel mimics the functionality of xargs, but makes it parallel. So we'll first talk about xargs, and I think it's been in some of the scripts that you've seen so far, but we haven't actually talked about it in class, and see what exactly does xargs do. Xargs is a way to convert standard out into arguments for an executable. And there have been several ways that we've talked about converting standard out into arguments. And so we'll see some of those and then see how to do it with xargs. But so Echo is our favorite test program, A, B, C, D. Echo, these arguments right here get passed to Echo. And one way, let's just run the ls command right here. All of this right here is the output, the standard out of ls. One way of getting all of this passed to the arguments of Echo is doing these $ and then the curly braces, or the parentheses. Echo ls like this. This runs this program right here and then takes the output of this program as arguments into Echo. And that's what we get right here. We're not getting the new lines because by default, Echo removes all white space. If we wrapped it inside of double quotation marks like that, then the double quotation marks means treat it all as a single parameter, and so we do keep the new lines here. So this right here is the main way we've seen so far of converting standard out into the arguments for an executable. Xargs is another way of doing that with a slightly different syntax. We can say ls, whatever the command is, so that we're going to pipe this command to xargs. The thing that comes to the left of the pipe is the thing that was going inside of the command up here, inside of the $ parentheses. And then the thing that comes to the right of xars is the thing that came to the left of this over here, so this command right here. xargs echo. And this just takes the output of ls and again puts it at the end of echo. What the important thing here is xargs calls this executable exactly one time. If we change that, so instead of xargs right here, it was parallel. Change this to parallel. Now parallel is going to call this command right here, whatever comes after it, once for every space separated entry of the output of this command here. So now when I do ls pipe parallel echo like this, there's going to be, I don't know, 15 or so echoes called independently, each one with their own individual arguments, and they all get listed down here like this. They're all on their own lines because each echo by itself outputs its own new line, and each argument is getting its own echo. With xargs, each argument is not getting its own echo. They have just a single echo, so they're all on the same line down here. So the takeaway from this is that in order to use the parallel command, the things that you want, the command that you want to be parallelized comes to the right, and then the arguments, like the however many times you want things to be parallelly run, comes to the left. So let's take a look up here at these commands and how parallel is working. So this right here is the command that we want to have run multiple times. If we were to look at so right now we're looking at the parallel version of the file. Let's look at load tweets sequential.sh and adjust the formatting so they're side by side. Down here on the bottom is the sequential :E. We see that it's sequential down here. And let's go down to the denormalized again. So we have Python. This is the whole command that we want to have run parallel, and the $ files at the end has our list of 10 different files that's created by this command up here. And so what we're doing in order to parallelize this right here, the actual command to the right of parallel, is exactly the same as this down here. You'll again have to modify the port numbers so that they match whatever's in your Docker Compose file. And then the parallel command right here will take whatever is the output right here and start one of these instances once for each one of these, in this case files, once for each one of these entries in this variable right here. So in this case, since there's 10 entries, it'll run this command 10 times, and it won't end the program until all 10 of those have run. So this time command right here is going to give us the time that it took all 10 of these to run in parallel. The parallel command is useful, or let's see, with the MapReduce assignment, we were not using the parallel command. Instead, to make things run in parallel, we just put the ampersand at the end of the program call to make it run in the background. The disadvantage of that is that we can't time the results because there's no signal that comes back to us when the result ends. But the parallel command right here does let us time the results. It will not return control to the to this time function until all 10 of these have completed, and then the time that's output will be the time of everything altogether. Talked about a lot of things right there. Are there any questions about that? Okay, so then the idea of this part of the assignment right here is you'll have to create a single command that takes a single file as input in order to do the denormalized, and then you will just put this right in front of that command so that it parallelizes it and runs it on each one of those files. That command, you'll create your own shell script that just runs this entire thing right here, passing in the parameter to the shell script as this location right here, and it'll load that shell script into the file. These instructions right here just say that same thing, but it gives you some ways to check to see if your shell script is working or not. My guess is that when you sit down and work on these problems, you will come up with questions, and so feel free to ask as you come up, posting them on GitHub or asking in class. That's it for today. Be happy to answer any questions that people have after class, or again, I have my office hours from 1 to 2 today. So see you all on Wednesday.